Okay, yeah. Thanks, Amrit, for the introduction. Yeah. Hi, everyone. Good evening. So, yeah, hope you are all doing well. So, we'll start the tutorial session. Okay, so the main materials that we'll be using for this tutorial are on this GitHub repo. So, you can see the link in the chat also in the Teams chat. So, if you open that, this should be at the top. Okay, so this particular link. So, you can go there now or after the tutorial, and you can continue working on these scripts. You can start editing from there to make your own solutions. Okay, so as you already probably know that this particular competition is focusing on the task of intent detection, and the dataset that we are going to follow is something called is the massive dataset by Amazon Science. The name of the dataset is massive. So the task of intent detection is basically goes like this. So in case of suppose you have a chatbot or as a mobile assistant like Google Assistant, where you are saying something to the system, and the system has to identify what is your request, what is your request type. So suppose you say that create an alarm for tomorrow morning, then the system has to convert that natural language text utterance or like what you are speaking into some kind of action. It can be like set alarm, one action that the operating system can handle. So your mobile Android system can handle that and actually create an alarm in the app, right? So this kind of tasks are handled by this intent detection family of models. So this, in general, this is a multi-class classification problem because you have different kinds of tasks that you want to handle using these sort of systems that you, and this can be for different platforms. This set of tasks that you handle can be different. So for example, for an Android phone, it can be something. But in case of a, let's say, a chatbot on some website, for example, SBI website, the intent that we want to detect there can be different, right? So that's why we need larger data sets and more capable models which can handle these different types of intents. Right. So that's why we need. Sorry, was there any question?
Please continue. I think that was someone just entering the room. Please continue.
So that's why we kind of need systems which can handle large sets of large set of types of intents to be identifiable to be. I think there's echo probably.
No, please continue. I think it was someone who has enabled the mic when they entered. Please.
Oh, okay. Right. So yeah, so that's why this massive data set was originally proposed. So this kind of covers many different kinds of intents and also different languages. So as you can see, this has this particular data set has examples in 50 languages, 18 different domains, and 60 different types of intents. So this can help you make a very generalizable model which you can use in different settings, and also if you want to fine tune it for newer tasks, it would be easier to do so. So that's why like this is a good starting point for you to build your models. And another thing to notice here is that if in this competition, a new surprise dataset will be given at a later stage. So this may have different languages or may have different intent sets to be detected. So you kind of have to do few short learning on top of the model that you have built using this initial massive dataset. Okay, so the first in this script we'll go over some like how to load this dataset, where to get this dataset from, and what are the properties of this dataset, what sort of information are available. Okay, so first at the top you can find the link to the Codalab page which will be hosting the competition, and also the link to the actual IndoML Datathon website. And the link to the dataset is given here, the massive dataset. So this is a Hugging Face page, so you can get this information from there. So now we first start by installing the datasets package. So this is a Hugging Face package. So Hugging Face is kind of a website or like a toolbox which provides various packages for working with NLP, newer models and datasets. Right, so they have kind of standardized various APIs that you can use how to load different kinds of model, different families of models. So they can be of different structure or different architecture like transformer, sequence to sequence, or language normal decoder only language model. But it allows you to use all these different pre-trained models using a single API. So that's what this Hugging Face package does. And it also has other libraries like datasets and evaluate, which helps you load different types of datasets and evaluate your models. So you first start by installing the datasets package. And so if you also go to the Hugging Face website, you will see like and search for this massive dataset. You will see a nice web page for that particular dataset, which gives lots of details about what sort of classes are there, what are the features that are present in this dataset, and how to load these datasets. So you can get these smaller code snippets also that will allow you to load this dataset. So many of these functions that you'll see below are kind of like I have obtained them from there. So for example, this snippet is usually available on every page of Hugging Face website. So when you go to any models website or datasets website, you can get this snippet for how to load that particular object. Right. So once you do this, it will automatically first download the dataset and also load it, like pre-process it and load it into a nice object which you can browse to. So this is what we are creating as the dataset object. Right. So now if you just try to print this dataset as like the whole object, it will show you different properties of the dataset. For training, you have around 587 utterances available. And so the features that are present in the dataset are also listed here. So first you have some ID. So this ID will be unique for all the instances in this overall dataset. It kind of helps you identify which instance you are looking at. Now, beyond that, the main important features that we have available. So one is local. Local is basically the language of that particular sample. So this can be like, it can be English, or basically the code, the ISO codes for English languages like EN, US, or some other language, Hindi, Bengali, so it will have particular codes. So that is the local. Then you have partition, scenario. So these give some information about when this dataset was collected, which particular worker was working, what was the scenario for that particular utterance being collected. So these metadata information are there, like partition, scenario, annotation, annotated utterance, worker ID. So these are kind of information that they got from the actual crowdsourcing process. And the main objects that we're interested in, one is this utterance. So this has the actual utterance text that was presented to the worker, and the intent was the class level that the worker assigned to this particular utterance, right? And in the annotated utterance, you have some extra information also in JSON structure. So you can use this information also to make your model better. So within each utterance, it also shows you like which particular span of text corresponds to some intent that you are detecting. So that has some extra information that you can make use of. So now you can also print. So if you just print this dataset object, so it will show you like the overall structure of what sort of features are there and how they are structured, what are the names of the fields. Now you can also look at more like further details of these individual features by printing like these features of the sub-object within the features field. So that will tell you what are the types of these features that are there. So for example, annotation utterance is a string, utterance is also a string. Whereas if you look at intent, it will show you like this is a class level, because this has to be a numeric ID identifying like which particular class it belongs to. And it also has like all the names of the classes. So date time query, and you can see like these are the intents that we are trying to detect. So date time query is like when you are asking your phone what is the current time. And other examples are like transport ticket. You might be asking your phone to book a ticket for a train or something. So that's this particular intent. So these like all these intents are there. So this the all 60 intents that are covered in this data set. Right. So now moving on. So we'll look at a few examples also. To access individual examples, what you can do, you can just call out the particular split that you want to look into. So for example, dataset train, and then you can give the index of the example that you want to retrieve. So this index goes to like basically 0 to till number of examples -1. So it's like you are accessing an array. And if you access it like this, you will get a dictionary with all the features being presented there. So for example, in this particular example, you can see like the locale is a Mongolian. So this is a text in that language. And you also have the intent ID. And this is the annotated utterance where you have like each of the items being detected, like in the what which span denotes which particular intent element it is detecting, which slot. And right, and the actual textual utterance is in the field utterance. So in the examples that I am showing here, we'll only use these two fields. One is utterance and the other one is intent ID. So we'll only use these two fields to build the models, but you can definitely make use of all the other fields that are there, like the individual judgments from different users. You can use this to create confidence, have a confidence level being predicted by the model. You can use the annotations of the utterance to use the slot information to like have a model which generalizes better. So you can use all this information. Okay, so now we'll look at a few visualization to try to understand like what is the statistics of this data, like statistical properties in how is the class distribution, how is the language distribution of this data set. So we load this data set into a data frame so that we can do this analysis in an easier manner. So it kind of loads in as a data frame table. And we'll be using the Seaborn package to do various plots. So you can use Matplotlib, but Seaborn is a package which kind of gives you nicer defaults to work with. So you can use this to get like very nice coloring and labeling by default. So you don't have to change many parameters. Okay, so now first we are looking at like the language distribution. So if you see like these are the 50 languages that are there listed listed together in the x-axis. And the distribution of them is like perfectly balanced. So the authors of the dataset has made sure that all the languages has equal number of samples in the dataset. So from this number of samples. Now, if you look at the intent classes, then you will notice that it is not as perfectly balanced in the language as the language now. So there are few classes which are like have very less number of instances. Like this particular class is like very probably below 100 samples. So there are several such classes. Whereas some classes you will have a very large number of samples. Okay, so captures or learns all the classes well. So that can be a challenge for you in this particular competition. And also from here you can get an idea of when you are given a few short surprising test set, how to simulate that. So you can do this by tweaking this distribution also. So for example, you can take the top like highest occurring instances as the data that you were available with you initially, and you can take the lower the classes which has less number of samples as your test set classes to create this kind of setting where you are training with a larger data set and then you have a few short scenario for evaluation. Okay, and so this plot is again the previous same plot. So this is just kind of sorted, and we have actually like written down what are the class names corresponding to each intent class ID. Okay, so this kind of tells you which are the most occurring classes and which are the like least occurring classes. Right. Okay, so that's basically the exploration of the dataset. Now we'll move on to actually building some models for this. So we'll be mainly using the Hugging Face package to build all the models, and they have very nice APIs which are called trainers. So using trainers, you can like avoid writing all the boilerplate codes for doing this sort of training. So when you are trying to train a machine learning model, you have to do various steps. Like you load the dataset, then at every update step, you have to take some batch of samples through the model to get like that do back propagation, to update the model at every step, then estimate the loss, validation loss. So all these things are taken care of by the trainer class. It trains your model, goes through the whole data set, then at certain steps, it will do the validation step, tell you what is the current accuracy, current F1 score, all these things. And so all these things are taken care. So you can use the trainer class. So it works very nicely with all the default models that are available there on Hugging Face. Now, if you were trying to build some custom model, so it might be slightly difficult to use the trainer class. In that case, you might want to use vanilla PyTorch to write out your training loop, or you can try to have a custom trainer class that you extend from the Hugging Face trainer class to build a new trainer that supports your custom model. Okay, so so there are two main functions or classes kind of which helps you load all these different models. So one is the set of classes called auto models, and the other one is auto tokenizer. And earlier I was mentioning you about like how Hugging Face provides you all the different architectures of models through a single API. So these are the main two APIs that allows you to load different kinds of models into like a same kind of functional API. So you can run the same function on different kinds of models and just expect it to work. Okay, so right, so just like before, we are again loading the dataset. So that part is same as before. Now we'll be using the multilingual BERT model for this particular script to train a model. And first we are loading the tokenizer, and we are doing this because we first need to tokenize the dataset that we have loaded. Now, if you are using the Hugging Face dataset class, there is a nice function called .map, which will allow you to just tokenize the dataset with a single call. Right? So you can just call like dataset.map and the tokenize function. So tokenize function is this function that we define. It just takes in each individual utterance and does the truncation as necessary to fit it to a maximum. So that's basically one step thing. So it will give you the tokenized dataset. Now, if you look at the tokenized dataset, so in addition to the fields that we had earlier, so these are the things that we already had, these features. Now, if you notice, it has added few other things: input IDs, token type IDs, and attention mask. So input IDs is basically the tensor form of your natural language text. So you had the utterance in natural language. So it has tokenized and convert them to their corresponding vocab IDs for this particular model. So these are like numeric arrays. So you can now pass this through your transformer model embedding layer to get embeddings, and it can do all the like normal processing that a transformer has to do. Right. So it adds these fields. And these are so input IDs will be your input to the model, and intent ID that was already there will be target for your transformer classifier layer.
So Bishal, one quick question. So when we select a pre-trained model, what all should we consider? What all should be the considerations, and how often do you find that performance difference varies when you compare, say, models of similar sizes, say, similar parameters?
Right. Okay. So yeah, so that is a good question. Actually, I have some comments here on the top for that. So yeah, like when you are trying to choose a model, so there are a few things that you should consider for this particular competition. One is that the data set is large, right? So to be able to train like a model on this large kind of a data set, so you need to have a model which like maybe the size is smaller or is able to train faster using less number of samples. So usually if you are looking at later generation of models, so models that have come up more recently, usually those will do better in terms of like how fast you can train or how less number of samples it can take. And also you need to consider the multilingual nature of the dataset, right? Because in this dataset you have these different languages. So you need to have, if you're picking a pre-trained model, you need to make sure that the model was pre-trained on some other languages also. So for example, here I have mentioned DistillBERT. So DistillBERT is an English only model. So if you take this model and fine tune it on this dataset, because the dataset is large, it will work. But the accuracy will not be that great, and it will take a longer time to train. So instead of that, if you take BERT-based multilingual case, so this is a MBERT model, multilingual BERT model. And if you fine tune this with this dataset, so the training will be much faster, and you will be able to reach this accuracy, like good accuracy level quite early. So these are something.
So if I use DistillBERT, wouldn't it lead to something like an out of vocabulary error, especially if I have, say, Arabic or some Indian languages in the mix?
Right. Yeah, so with WordPiece, it might lead to some error. So if it was like a BP tokenizer, I think it could have handled. But if BERT is WordPiece, as far as I remember, so it can lead to some out of vocab. But although I have processed this whole dataset actually using this particular tokenizer, and it seems to work. So yeah, DistillBERT
is like it's not multilingual, but still you're saying there is no out of vocabulary error.
There was no out of vocabulary, so maybe it is just tokenizing at character level in the end for the other languages. So there could be a lot of loss of information there. So yeah, the main thing is you should probably not use distill, but so something multilingual is recommended. Right. So yeah, another issue, like the issue with the large scale thing is that, so this dataset is very large. So if you want to use this full dataset to do the training, then you have to also think about whether you want to do like full fine tuning of a large model, which will take longer time, or you might want to take a very good base model, which is like multilingual BERT, or the later one model that will show later, or do like linear probing on top of that. So linear probing is like you do not fine tune the whole model and just fit a linear classifier layer on top of that model. So this will be much faster because you don't have to do full backpropagation, right? And there are also newer models which can allow you to do faster training, like PAFE and low rank adaptation allows you to use less amount of data and less time. It takes less GPU memory and less time to fit the models. Or you can look into distill models that might be available. So usually you can just search on Hugging Face for a particular model name. Suppose you want to use Roberta, you can search for Roberta distill. So usually there are checkpoints available. People have distilled these models to a smaller size, and you can use these things. And I have given like two such list of examples. So actually these two lists kind of gives you examples of models also as your starting point. So this will kind of allow you to avoid this initial fine tuning phase, and you can just focus on how to make this work on the few shot setting that you might be getting later. Okay. Right. So I hope that clarifies the model selection. Okay. So right. So where are we? So we are looking at this example. So once you have tokenized, you will have these extra two features, and we'll use the input IDs column. So this input IDs is the feature that we'll use as input, and intent will be your class level. Okay. Now, so I have just given a reference to data loaders here, although we are not using it. So data loaders, so once you have the data set, you might need data loaders to create batch of data sets if you are using like a normal PyTorch training loop. So in that case, you will need this particular snippet to create data loaders out of this Hugging Face data sets. So you can use this snippet in that case. So now we are actually loading the this embed model. So for embed model, so this so we need it for sequence classification, right? So the type of the task we are handling is you have input utterance and you want to classify it to some intent classes. So the main auto model class that handles this kind of tasks is called auto model for sequence classification. So what this does, it loads the model that you have, and it automatically attaches one classifier layer on top of that. And it also takes in the num classes, so it will create the classifier layer according to what number of classes you have. So your model instance is fully created here. So it has like the pre-trained base embed and a classifier layer on top. So beyond this, the training step is basically defining the training arguments and the trainer class. So for creating the training, so for the training step, you need two things. One is the training arguments. So this defines all the hyperparameters that you need for that you need to specify for the training process, and there needs to be a trainer object. So this handles the actual training loop that happens. So it goes over the data set batch by batch and does the backpropagation gradient descent updates. So here we have specified a few different parameters, like we have set the what should be the batch size, number of epochs. You will probably want to have more number of epochs than 2. So just for the sake of example, I have set it to 2 here. You can give certain logging instructions. So you can tell, and the main benefit of using the logging step here is that you can use weights and biases or W and B to log. So this kind of creates a very nice page on the WNB website where you can track how your training is progressing. So you can just set report to equal to WNB here. So that will automatically log to WNB website. right? And you can also mention various learning rates and other things here, like what is should be the learning rate, and if you are using whatever optimizer you are using, what should be the parameters of that. So for example, by default it uses the Adam optimizer, and you can specify the warm up rate and the weight decay rate, right? So it's a Adam optimizer with weight decay. So there are other parameters that you can set. So you should, so it's always recommended to, once you have like gone through the script, you can always look at the documentation of these particular APIs. So it will give you a very nice list. Hugging Face has a very nice list of all the parameters you can set. Okay, so now once you have the training argument set, you can create the trainer class. So it basically takes your model, the arguments that we set earlier, and you have to specify what are your training and evaluation data set. So it will use this for training and calculating the validation F1 score. Right, and you have to specify the tokenizer and data collator. Okay, so we had created a data collator earlier also. So I'll just quickly show you that. So this comes from the tokenized, so data collator with padding. So what data collator is does is that you will have sequence of different lengths, right? So when you tokenize, so data collator will automatically add padding tokens to the end of this tokenized sequences, so that you can create a matrix or a tensor out of this. So your input tensor for these models need to be of size batch size comma some dimension, and this dimension needs to be fixed. So you cannot have variable sequence length. That's why we need to specify a data collator which will do the padding. So that's taken care of by this. And that's actually the end of what you need to do for setting up. So after that, you just call stats equal to trainer.train, and it will start training. And given like whatever eval steps you have given specified in the training argument, it will continue to evaluate after certain steps, like at every 1,000 step it is evaluating on the validation set, and beyond that it is doing the training. Okay, and for computation, for the metric that you need to use for evaluation, so we have defined a compute metric class, and we are getting this metrics from Hugging Face evaluate package again. And so we'll recommend using macro F1 score because the dataset is imbalanced here. So if you use accuracy, it might focus on the more occurrent classes than the lower classes with lower number of samples. Okay, so you should avoid using accuracy, and better if you use the macro F1 score. So it kind of nicely considers the F1 score for each individual classes and then averages the score. Okay, so yeah, once the training is done, you can like print the evaluation metrics using like trainer.evaluate. So this will run a final evaluation on your validation set. And if you want to do like a full evaluation, so then you can load the validation or the test set for the final evaluation, and you can get your stats from there also. Now beyond this, so one particular thing that we have done here, so which I kind of skipped earlier. So if you notice this part, so we are sub-selecting only these 4 languages for training. So so I did this. So I just wanted to show you here the effect of using a multilingual pre-trained model. So suppose you only had dataset for these particular languages, and you have very few samples for the other languages, or you didn't have any sample for the other languages. So then if you are using a multilingual pre-trained model, then you can just fine tune on a few languages that are there in your intent detection dataset. And just by using that, you can get a good performance on the other datasets also. So so we are now again evaluating on the actual, like the full validation set. And if you see the performance here, so we are training only with this Bengali dataset, Bengali, English, Hindi, and so I think there are some 4. So if you see the performance for these particular languages are very good, which is expected because these are the languages we have specified for training. But if you see the other languages which we had omitted from the training set, there also the model is able to get good performance for quite a few of the languages. Right, so this kind of shows the benefit of using a multilingual or a good pre-trained based model. So this will allow you to transfer, like even having a smaller data set to train and transfer the performance to other languages or other intent classes with very few or even 0 samples. Okay, so yeah, so this is the first script for transfer, like fine tuning an actual model. So then in the next part, we will see a large language model fine tuning. But if you have any question in at this point, you can ask, because we'll move to a different kind of modeling beyond this.
So I hope everyone can, the mic is enabled for everyone. So please make most of the opportunity.
Yeah, and you can also probably post in chat if you don't want to use them.
I think Manoj has a question.
Yeah, I'm asking that the data which we get from the that website, it didn't contain the column intent.
No, actually, it contains that column. So you are talking about when you are loading the data set, right?
Yeah, yeah.
So, so here is the intent feature actually.
Yeah. So
But
Manoj,
but
yeah. So Manoj,
yeah.
it was actually given in a separate file called as solution. So we have a post in Discord. So Shubhadeep, can you clarify on that? What was the exact difference between what we have done and what is available in other place? Shubhadeep, are you there? Yeah. So Manoj, what we can do is that you can just contact me via Discord. I assume you are already in Discord. I can point you to the relevant post that details about this. Does that work for you?
Okay, sure.
Okay. So that's where the data loader that Bishal was showing will be helpful, because we see what Bishal is showing is that this data is already available in Hugging Face library. But if you want to load it as a custom data set, you might have to use the data loader. So that's where that functionality can help. Okay. So I think Kaustubh now has one question. Kaustubh, please go ahead.
Hello, sir. So, am I audible? Yes, I wanted to confirm about the dataset available on the Coda lab. I think so. There is some mismatch in the there is one class missing from the validation dataset. While I was training the dataset, so this issue came up with me while resolving of the classes. So I just wanted to confirm that is it from my side only, or is it just might be a small error? And
So Kaustubh, I think the original dataset itself has some information missing, some of these classes missing. So that's an artifact of the dataset. It's not an omission per se. But I believe even with that, you will be able to upload the files and get the relevant information. So were you able to like evaluate it properly? Like, are you facing any roadblock or bottleneck with that issue?
Actually, yes. While using the validation test, my classes mismatch. There are total 60 classes in the test data set, and in the validation set there was only 59. So my model was showing some kind of issues with that. But
Okay.
I rectified it by using some of the classes from the main test data set only, just to be sure about that it's running. But right now also I came up with this thing that sir has told about the data set from the Hugging Face. Most probably I'll be using that.
Sure. Yeah. So we are using the same split. That's not a problem.
Sure, sir.
Only thing is that when you submit the files to Codalab, you might have to look into the IDs. We have generated unique IDs by concatenating the language code and the unique identifier within the language code. So you might have to consider that you have to add one extra column. That's all.
Sure, sir.
Yeah, sure. Thanks. So,
Okay.
Bishal, I have one quick question.
Oh,
So, yeah, so one thing is that, like, how often do you find that this using of auto model versus say specific? So we generally do auto model auto tokenizer, which makes it very convenient. But
right.
sometimes the same model might have multiple tokenizers implemented within Hugging Face. Some one of them being faster, other being more efficient. Or so how
Right.
often do you find that this giving too much control to the system versus we manually selecting this? How often that differences matter, or is it negligible differences?
Right. Actually, it depends mostly on the so in Hugging Face, so each of these models are kind of specified by a URL kind of like tag, right? So it depends on the config that was provided with that tag. So for example, here we are using this default embed models tag. So this BERT-based multilingual case. So for this one, it automatically picks the fast tokenizer. So there is an efficient implementation of the BERT tokenizer. It will pick that correctly. Now, if there are some model which says some person has defined, like fine-tuned themselves and they have uploaded the checkpoint, and you want to use that. So in that case, using the auto tokenizer may give you the older version of the tokenizer, like normal BERT tokenizer, and it will not give you the BERT tokenizer fast. So in that case, you might want to manually load the fast tokenizer and work with it. In general, for the popular models, it's usually taken care of, but some models might be there which are not like that much used, and the authors may not have updated it to use the fast tokenizer.
So this might be taken into consideration, especially you have provided the list 1 and 2 where it is fine-tuned for our particular data set. So there they might face some issue on that line, right? So that's something
Right.
we need to
So
consider.
actually, yeah. So if you want to handle that, I'll show you like how to. So suppose you are searching for a model, let's say BERT-based uncased. Although I don't know if they show this anymore. They used to show this here. So now in the documentation also they are kind of recommending this. Okay, let's see. Master. No, I was looking for the class. So yeah, I think they handle it. So there are classes like there is one way to check this also. There is one point where I can show you this example. So you can check at least which class is loaded. Usually it is the correct class. The only problem is you might face with the tokenizer part. Checkpoint. Okay, so it's not exactly in. So right now I have not shown this. So if you just take this model and create a cell where you are just printing this model like this. So it will tell you which class it has loaded. And from there, you can manually check whether the tokenizer is the first one or not. Then you can manually try to do that. So you have to print either the model or the tokenizer. So if you just print that, even though it was loaded with auto tokenizer, it will have the actual class mentioned here. So from there, you can check.
Thanks.
Yeah. So if there's no other question on this part, so I'll go on to the last one. Okay, sounds good. Fine. So yeah, the last one will be, I'll try to do this quickly. So this is basically the newer trends that have been set by prompt engineering. We just wanted to showcase one example of this, how you can try this approach also. So you might have heard about in-context learning or prompt engineering by now, and this has become famous with mainly with ChatGPT and GPT-3. But nowadays there are many open source models are available which can do this sort of in-context learning and prompt engineering better, or like comparable or even better than sometimes GPT-3 or ChatGPT. So you can use these models for solving this task also. The benefit being is that you won't have to train these models as much. So you can use these models zero shot sometimes, or even like just fine tune a little bit using a few samples and then just so as to show it examples of all the classes, and beyond that just use these models. Although like in prompt engineering, so the main effort that you have to put here is how you design the prompts, right? So what I mean by prompt is this. So let me just go to this. Right. So this is how a prompt will look like. So this particular part of the input. So if you see, I have printed a string. So this whole thing is like one string. So at the beginning of the string, I have described what the task is. So detect intent of the input utterance. So I'm telling the model, so this is the task it should perform. And these newer models, so these are usually instruction fine-tuned models or very large-scale language models, which has seen enough natural language data during its pre-training so that it can understand these instructions. So I am kind of exploiting this nature of this model. So first I'm saying like this is the task, and then I'm specifying all possible classes are these, right? Because I like if I try to give example of all these classes, so there are 60 classes here, it will be very like a long prompt. So I have just taken this approach, all possible classes, and I have listed like all the 60 classes here. And this is just one example of a prompt, right? So you can change this input task description. You can change how you are giving this listing all the classes. You can list all the classes. You can just give examples of all the classes like with one utterance. So you can have various ways of providing this information, and this is where the main effort goes to. So if you are using prompt engineering or in context learning approach, you have to figure out which particular prompt style works better, which way, like how many number of samples work better, or which samples you should give. So for example, instead of giving all these like different samples from different classes, you can try to see like the input utterance you have for like as your query, which is this particular utterance for which you don't know the intent and you are trying to ask the model. So for that, you can try to find out similar utterances to that. So you can embed that utterance and do a retrieval on your dataset. Right. So there are many different methods that you can follow. So these, like if you just do a Google search on how to do prompt learning or prompt engineering, you like see like whole set of blogs, like hundreds of blogs on this. Right. So this is the main effort that you have to give if you are using this approach. And if you're using this, you don't need to train the model. It often works like without training, just through the examples that you are giving. Okay, so the model that we are using here is this Bloom model. So this is a Bloom called Bloom Z. So this is like an advanced version of the Bloom model, and I have described like how this was trained here. So the Bloom model originally was a large-scale language model, like 175 billion. And the Bloom Z model, they have fine-tuned that particular large language model on various human instruction dataset from different languages. So it has coverage of I think some 100+ languages, and it was taught on various cross-lingual tasks. So this particular dataset. So this particular dataset, this XP3, has is a dataset where you have various instruction examples of instruction of cross-lingual task where you are asking the question in one language, the answer might be in different language. So this Bloomsy model was pre-trained on that to give it multilingual capabilities and also instruction following capabilities. So that's why we can use this for different tasks. So I just mentioned it to do intent classification. It will be able to handle that classification task up to some extent. Okay, so this is the model that we are using. Now, one thing to notice here is that this is a very large model. So this is a 3 billion model. So there are even larger models for this, like 7 billion, and the largest size is 175 billion. So you cannot expect this to load on if you are using like Google Colab or some other resources like Kaggle notebooks, right? So there you have very limited resources. So it will be like a 16 GB GPU or at max 2 16 GB GPUs. So in these cases, you need to make sure that you can load the model so and the model fits in this single GPU, and while inference also. So if you are doing very long inferences and your sequence is very long, it can ask for more GPU RAMs, right? So that's why we are using this particular feature called 4-bit quantization. So this is a new feature that Hugging Face provides through some packages like Bits and Bytes. What it allows you to do, you can load these very large models, but do the computations only in terms of 4-bit floating point or 4-bit integers. Right. So there are other modes available also. You can load in 8-bit or 16-bit also. So there are different modes. I have loaded here the smallest mode here because otherwise this model will not fit. Right. So once you do that, you will be able to run this particular model and do inference on Colab also without any. There should not be any problem unless you are trying to like extend the batch size or something. Okay, so now once you do that, so the next extra step that we have done here, so we have done a little bit of pre-processing on the dataset. So earlier we were just tokenizing the dataset and using the intent feature as class, but here we need to construct the prompts also, right? So for constructing the prompt, we have this function. So again, like using the dataset API from Hugging Face gives another advantage. You can apply these sort of modifications very easily. So we are doing a pre-processing and adding a new feature to the dataset. So we just need to define a function which takes one example instance and adds any feature, like anything you want to add. So just like this. So example prompt equals something you are trying to add. So here what we have done, we have added the task instruction, prompt exemplars, and then the query. So utterance followed by the current utterance that we have in this example, and then we end at intent colon. So this is kind of like the query point. So we are trying to prime the model to predict the intent only. So if you don't give this, it might generate some random utterance or random things. It will start producing long text. So you have to kind of make sure the model predicts what you want it to do. So that's where we have constructed like this kind of examples first. So in the example you are showing, so when the prompt intent is there, you should just predict the class and nothing else. So this kind of primes it that way. And we are also giving a task instruction, which is priming the model also to do this intent classification task. So we are kind of trying to drive the model towards doing this task. Okay. So in this part, we are adding instruction, exemplars, and the utterance, the query utterance and intent prompt. So this is the few shot case. So there can be a zero shot case also, where you just give the task instruction and do not give any examples. So the benefit of this will be that the prompt will be shorter, so you will be able to do the inference faster. So if you are loading very large models, then the inference will also get slow. So in that case, using zero shot prompts might also work. So you can check that. And once you have defined this function, you can just call this again with this map function. So you saw this map function earlier with tokenization, right? So you can use this with any function. So you have defined the add prompt function, and we just call it on top of validation, and it will extend the validation with this prompt. So if you just look at the first example from extended eval set, you can see like the prompt feature has been added. And this has the structure that we wanted, like detect intent of this, all possible classes are these things. There are a few examples also in between, I think. So here are a few examples, the utterance intent, and then finally the query is there. Okay. So this is the general paradigm of how you construct a prompt. So you can change anything to your liking here, and you can figure out what works. Okay, so now once that is done, what we have to do, we have to do inference on all the samples. So we have loaded the model already, so we'll just directly go to the inference step. Right. So this is the inference step. So we are loading the eval subset that. So okay. So we are again creating a like smaller subset because it takes long time to run. So when you are doing the final submission, you can change this to any eval to like the full set, or you can just use the extended eval set there. But anyway, like we are creating a subset here which has all these features. So the first thing is we take out the prompt and tokenize it. Right, so we are tokenizing the prompt and not the utterance anymore because we want to pass the prompt to the model, and then we call the model.generate function and pass in this tokenized prompt, right? And we are also giving some extra inputs. So instead of generating one sample, you can do multiple sample generation. So it will kind of give you multiple options, and among those options, you can see which was the most occurring prediction, right? So this can give you some sort of confidence also, which is like added benefit. And you can like omit this part also. This is not necessary if you're just doing one prediction. And once you have predicted, so this y will have so y will look something like this, right? So this was our query, right? So in query, the final intent was not there, and we are asking the model. And this part is the generated output, which basically what the y variable holds. So as you can see, it has detected some intent and given that it should be IIT underscore coffee. So this should be the class. So what we need to do, we need to just parse out this generated output and parse this particular, the ending part from this, and that should be our prediction, right? So predictions. So you have this parse function. It takes what was your input prompt and what is your output text, and basically splits it. So it takes out the initial part, whichever was the prompt, and then splits it by the next new line occurrence, and assumes that has to hold the predicted class, right? And then you have, okay, so here is another important thing. So since this is like open-ended generation, the class that it predicts can be anything. So even though we have mentioned what are the valid classes that it should predict, it can predict some new classes also that it thinks should be suitable. So you need to make sure that this is there in your level class, only then use that for prediction. Otherwise, you should not use that as a prediction. Okay, so you can assign like a different class number to that, which is not there. Okay, so once you have these functions, you apply that and you have like the final parse predictions, and this kind of shows the all three options, right? So we have generated three options. So in that three cases, we have these three predictions. So as you can notice, the predictions here are not good, and you need to do a little bit more like prompt engineering to get this to work better. Or you can use a better, like larger sized model or a different model. So instead of Bloom, you can use some other model like Flantify or Falcon to do the predictions, right? So not all models have these predictions. So you can just take a look at how the results were. So remember that we did not have any training involved. We just tried to do this like vanilla through using the model, pre-trained model that we had, and we are just prompting it, right? So if we get any good prediction, so that's like an added benefit. So if you see, like it's not very good, the performance, but for certain languages, it was able to go like 20% performance, like above 15% F1 score was there. So it's not a perfect model, and you can do like prompt engineering and try out other checkpoints to try to push this up higher. But this is also a solution that you can try out. And if you want to fine tune also, you can like take a few examples and fine tune, because these are large models. It will not be easy to fine tune them. So you can do like a small fine tuning and see if that also helps in this prompting performance. So yeah, so that kind of ends this part. So if you have any query on this part or in general, you can ask.
So I have a more generic question, Bishal. So one thing is that if you see, like prompt engineering is in a way, it's like your ability to search in the web, right? There is no fixed way of doing something. You eventually acquire certain skills which are not quantifiable. You are good at searching something, some people are not. So, so the question is that when do I decide that maybe I don't get much from the prompt engineering? Maybe it's time that I have to do fine tuning. Like when do I make that decision? Typically, or anyone make that decision?
True, yeah. Actually, also this, so other papers are there which have worked, which have shown that you can do fine tune the BERT kind of models which are smaller in size, fine tune with them a type of instruction on which you want to work with. So it can be instruction of intent classification, and since it is not like a classification task anymore. So in classification, you are training a new layer. But suppose you have GPT-2 model, which can generate text. So if you fine tune that for the instructions of your task and show it certain kinds of instruction examples that you will give, then these smaller models can also work well. And using those kind of fine tuning steps, you can kind of control with which instructions it can work. So you can have more control there if you want to fine tune a little bit some smaller models and do instruction fine tuning. So yeah, like there are some, so basically you can think out different ways to how to make this model work better with any kind of instruction and a bit robust to the prompt strings.
Got it. So I think we have a question from Dhruv via chat. So Dhruv, you want to ask that directly? Yeah, sure, please go ahead.
Hello, am I audible?
Yeah.
Yeah, so I just had the question because we have been working with transformers for a bit right now. And yeah, I was just wondering if there were any more advanced techniques because I have not been exposed to them in the past. And generally, the trend in Kaggle competitions goes that you have to employ some ensemble methods to get good results. So, are there anything that we can look into with regards to this task?
Right. Yeah, so this is a very good question. In Kaggle, you will mostly see it's either ensemble of methods or some XGBoost classifier that is winning the competition. So basically in Kaggle, so this trend is there. So if you have NLP kind of task where you have like a larger data, slightly larger data set, not very small, and you have to do like classification or generation. So they are usually ensemble of different types of models, like pre-trained models works best. So people will use say Robota, let's say Robota, GPT-2 and Debata. So these 3 or 4 types of models, fine tune them on this particular task and then ensemble their output. So then like this is a very simple pipeline. So you can just train different models. You will have their own accuracies and you can do like ensembling, like max voting ensembling or a mean ensembling to get your output. Right. So this should be simple enough. But to work with a gradient boosting kind of technique, so that becomes a bit tricky because so the structure of this competition is slightly different. So you have a very large training data set available at your hand, and also you will have few short examples at a later point. So I don't know how much gradient boosting techniques might help, but you can definitely like you can extract features from transformers and use them as your input to the XGBoost classifier or something. So that you can think of, or you can create some your features and create a XGBoost classifier which is part of your ensemble, right? So you have transformer based models and then you have gradient boosting based tree or random forest based models. So you can like have an ensemble of all of this. But yeah, there is no end-to-end approach for, if that you might be asking, like end-to-end approach for having the transformer model and some tree-based model connected together. So that is not easy to do because like tree-based methods are not differentiable, right? So you cannot really do that. So,
Understood, sir. Thank you.
I think there's a question from Basavaraj, which is I think for the organizers. So the question was about the CodaLab link. Yes, the CodaLab as a platform, it's a third-party platform. It's down. So we are in touch with the platform team and hope to have the platform as app. So yeah, so please bear with us until then. But as far as Massive is concerned, most of like you don't really require the platform. You have the validation data, you have the test data, you can do all by yourself. But for the surprise data set, we will require the platform and we hope to get it up. So yes, Basavaraj, you wanted to add something?
Yeah, good evening to the organizers and the speaker. I actually enjoyed the time over here and listening to the explanations. Thank you for that. I actually had a question for Bishal. So I wanted to know, like you were talking about the custom data loader. Now we have these pre-trained models. So these have been trained using a particular type of data which is being input to these models, right? Like if they're inputting only one sentence using that tokenizer for that model, so it has been trained using a particular uh, type of setting for that data set. Now if I want to use different type of features from the data set that you are providing, like you told we can use different features that are present as an input for these pre-trained models. How can we do that? Because it will only accept a single sentence as a tokenizer if it had been trained on a particular type of pre-trained model. it won't accept any other kind of input, if you're getting what I'm asking.
Yeah. That is a very good question, actually. Yeah. So, how do you use these extra features that we have? Right. So, okay. So, if you notice the model that we fine-tuned, so that was an embed model, but it was not originally for the intent classification task, right? So we tuned it for intent classification that task, and the effort that we had to add there is the classifier layer. So all these pretend models that are there, you can always use this like a core of your overall architecture that you are trying to build. So in this case, suppose you have this intent class, and then you have the annotated information that you have. So let me just refer back to the example. Lost the example. Right. So here, if you see, like, let's consider three things. So you have the annotated utterance, then you have the intent, and the actual utterance, right? So it is kind of well known in deep learning that the more data you have, the more number of training instances that you have, the better, right? So if you think about it, the intent classification gives you one task and n number of samples for it. Now, if you also consider the annotated utterance, which has the like the slot information, that gives you another task that you have to morph this input text into this labeled kind of thing. So wherever the words are certain slots, you have to specify them in this structure. Then you also have this slot method information, right? So this kind of gives like what are the slots present. So using this, what you can do, you can create different tasks for the same model architecture, and you can like add basically the necessary layers that you need. So for example, if you are using embed, then what you can do, instead of just classifying for intent, you can create a joint classifier where there is one classifier layer for intent, another classifier layer for the slots. Okay, so this is one approach that you can do. Now, suppose you are using a generative model like the Bloom model, or say you are using GPT-2 model. So in case of GPT-2, what you can do, you can actually even pre-train using this model. So you create the inputs in this way. So the input is only the utterance. And beyond that, the model has to decode all this information. Like the model actually has to annotate. So it has to first tell what is the intent class. So suppose this is travel inquiry. So you can say the utterance followed by say a comma or semicolon, intent equals travel query, then again semicolon, give the annotated utterance. So annotated utterance equal to this. Then you can mention slots where this. So this kind of gives like a data set which makes the model extra like utilize more features available in this input utterance. So it can help the model to learn things jointly, and usually these tasks are connected, right? Intent detection, slot detection, these are all connected. So it gets more signals to learn from. And for usually for these things, you have to add a few layers, add a few classifiers, and like accordingly tune the losses. Now for this, when it comes to the data sets, you have to change the dataset class true. So if you're just using the massive dataset from Hugging Face, you can add more features here. Like you can have one utterance for training, which has this extended form that I explained. For GPT-2, you can use like combination of textual format of utterance, intent, annotated utterance, all these things. And if you want to do this for, let's say, classification, joint classification, then in your model you need to add the layers, and in the dataset class you have to make sure that you are producing all the necessary labels. So that will be label for intent and also label for the slot method, right? So does that help you understand like how you can achieve that?
Yeah, I got the approach. I would like to add a point over here. Like you are talking about merging 2, 3 different techniques for the same pipeline. Now, when we do this, it's very computationally expensive. And while I have been training multiple times these different kinds of models on transformers, I've seen if we don't have the resources that require to build these types of complex models, it crashes. Hugging Face. So, do we have a way around it to train it in a way that it is computationally less expensive and we also get our desired complex model?
Right. So, okay, so there are few newer methods that have come up. So since these models are getting very large, it's a common problem that how we fine tune. So even if you have GPUs, it's very like resource consuming. So what you can search for is, so there are methods like low rank adaptation or fine tuning quantized models. So I gave you this example in the LLM situation, right? So since we can't load this model, we loaded it in a 4-bit setting. Right, so this 4-bit setting helps it in doing inference of from a very large model, because it is just using one, so like 32 by 4, so that's 8, right? So 8 times less GPU memory for your inference process. So you can achieve this for training also. So in training, there are like few extra steps you can follow up on Hugging Face blogs. So you can, okay, actually I have linked one thing. So in the repo, you can see this, the Falcon Collab link, right? Falcon Collab 7B. So they are actually fine tuning a 7 billion parameter model on Collab. So this is one example of how you can use these newer methods of quantization and low rank adaptation to train very large models. And even if this gives you difficulty because the data set is large, you can try to load their 3 billion parameter variant or 1 billion parameter variant so that the training is a bit faster. So there are methods that you can get help from.
Similar to LoRa, even adapters can be written, right? Where you add adapters.
Yes, yeah. So adapters also will help here, because it will help with the sample complexity also, how much data you need for training.
All right, thanks, Vishal. I'll look into it and see what I can do.
Any more questions?
Yeah, by the way, like if you have any doubts about the tutorial or anything, you can post issues on the repo. I will try to answer there also if you have any doubts specific to the tutorials or the like APIs that I have used in the tutorials, how to use them or anything, you can ask.
Can the Discord link be shared? I don't have it actually.
I see. So give me a minute. Let me share that.
So it's active discussion on Discord, right? Or we have some Google group.
So we have a Discord link this time. Let me share the invite. So you can access the chat, right? So
Yeah, let me check.
Yeah, I have shared it. So if there are no further questions, let's thank the speaker. So Bishal, this was really a comprehensive overview on different ways to approach the problem, whether it is compute intensive or in a bootstrap or in a very low setting. So yeah, thanks a lot, Vishal, for the time. I think this helps a lot of people to start, because most of the time it's an inhibition, or it's basically like, the overall setup looks intimidating to a lot of us. So it becomes very easy once we have a walkthrough. So that's really great for your effort. And yeah, thanks a lot. So let's thank the speaker, everyone.
Yeah, thanks for inviting and thanks for attending also. Yeah.
Thank you, Vishal. This was really informative.
Thank you.
So thanks everyone. So I believe everyone have access to the Discord and the event. Everyone is aware of the event. So please do try to make most of it. Yeah, so hope to see you next week. So next week, Sunday, we will have one more talk lined up. So hope to see you all. We will share the link soon again in all the possible channels, but mostly try to subscribe to our Discord server where most of the announcements come up. So Thanks everyone. Thanks for your time, and thanks Bishal once again. Yeah. Bye. So is Firefly's AI a real human or is it a bot? Are you there? Okay, I think it's probably, I'm not sure. Yeah. Okay, so thanks everyone.